Have you ever wondered how engineers can predict the future? Well, they don't use a crystal ball. They use something way more powerful. Today, we're diving into the incredible software that lets them see how their designs will behave in the real world before a single piece of metal is ever even cut.
Just think about that question for a second. The stakes here are just impossibly high. You have to know for a fact that a brand new design for a massive aircraft wing can handle the unbelievable forces of flight. So how do you test that without spending millions on a physical prototype that you're just planning on destroying anyway?
Well, here's the answer. You don't build it in the real world first. Nope. You build a perfect one-to-one digital copy, what we call a digital twin. And once you have that, you can go wild. You can push it, pull it, heat it up, and bend it in a totally virtual environment to find its absolute limits, all from the safety of your computer.
Now, the magic behind all this has a name: finite element analysis, or FEA for short. The best way to think of it is like a physics engine for the digital world. It takes a really complex object and digitally slices it into millions of tiny, simple pieces. By calculating how each one of those little pieces reacts to force, it can build an incredibly accurate picture of how the entire thing will behave.
So you can imagine when the stakes are at their absolute highest. We're talking industries like aerospace, where failure is not an option, or the automotive world, where safety is everything. Engineers turn to one of the most powerful FEA tools on the planet, a software suite called Abaqus.
Okay, so how do you actually go from a totally blank screen to a fully testable digital twin? Well, it's a pretty structured process, and Abaqus is there to guide you through every single step. Let's walk through what that looks like. First up, you start with the part. That's basically the digital blueprint of your object. Next, you have to define the material properties. You got to tell the computer, is this thing made of stiff steel or is it more like flexible rubber? After that, you set up the physics. This is where you tell the software where you're going to push on it, where you're going to pull, and which parts are bolted down. But honestly, the most crucial step is the mesh. See, the software can't solve for one big, complex shape all at once, so it breaks it down into thousands, sometimes millions, of simple little geometric pieces. By solving the physics for each tiny piece individually, it can accurately predict the behavior of the whole complicated structure. So, the digital twin is built. The physics are all set up. Now it's time for the main event. It's time to run the simulation. This is the virtual gauntlet, where we're going to unleash the forces and see if our design can actually handle the pressure.
You hit that submit button, and the computer just gets to work. It starts churning through complex physics equations for every single one of those tiny elements in the mesh, calculating how each one stretches, compresses, maybe even heats up. It's this massive number-crunching task that ultimately predicts exactly how the entire object is going to respond to all that stress.
And after all that analysis is complete, you finally get the results. And they often look something like this: a vibrant, colorful 3D model. But trust me, these aren't just pretty pictures. These are data visualizations that tell a really critical story. These colors really do tell a powerful story about stress. The hot colors, like red, are your warning signs. They're pinpointing areas of really high stress that are potential points of failure. On the flip side, the cool blues show you where the design is totally safe. So with just a single glance, an engineer can see exactly where a design is strong and, more importantly, where it needs to be beefed up.
But it's not just about the pretty colors. It's about incredible precision. The simulation gives you hard numbers. For example, it can predict that this specific part will bend by a maximum of 2.15 millimeters under a certain load. That is not a guess. It's a calculated prediction. This is the exact kind of data engineers need to know if a design is going to work or if it's going to fail.
So we've seen the whole process, but what does this actually mean for the products we use every single day? Why does all this matter so much?
Well, the impact becomes crystal clear when you compare it to the old way of doing things. Building and physically destroying a prototype isn't just ridiculously expensive and slow, it also gives you very limited data. With virtual simulation, you can run dozens of different tests in a single day for a tiny fraction of the cost. And that speed, it doesn't just save money. It unlocks a level of design iteration that was totally impossible before. It lets engineers find the absolute optimal solution, not just one that's kinda good enough.
And this power, it really does transform the world around us. Think about how safe your car is. That safety has been perfected through thousands of virtual crash tests. What about the fuel efficiency of a modern airplane? Well, that's thanks to engineers using simulation to shave off every possible ounce of weight without ever compromising strength.
It's the invisible science that makes our world safer, more efficient, and way more reliable. So ultimately, it really all comes down to this. Tools like Abaqus give engineers the power to innovate and push their designs to the absolute limit, all while making absolutely certain that the final product is as safe and reliable as it could possibly be.
And that leaves us with a pretty fascinating thought. As these digital crystal balls get more and more accurate, allowing us to see every potential flaw before it even exists, what does that unlock for the future? What new designs, the ones once considered way too risky or complex, are now finally within our reach?